Hello students, welcome to our next set of discussions on the concept of optimization as applied to infrastructure systems. So far we have familiarized ourselves with various approaches of optimization in general, including unconstrained optimization, constraint optimization with equality and inequality constraints, where we spoke about Lagrange multipliers and Kahan-Tucker conditions. So, in this particular lecture, we are going to introduce a new paradigm of linear programming problems, and we will try to motivate what is the need, how does it help, how would the solution look like, and in subsequent lectures, we will dive into the detailed methodologies associated with solving linear programming problems. So, again, a quick recall. If you remember that when we were talking about Lagrange multipliers, we were talking about problems which are maximize or minimize as they are equivalent with minus sign, subject to certain constraints, and we started with equality constraints where we formulated our Lagrange function L as function of f and introduced some multipliers lambda, and we spoke about the necessary condition and primal feasibility condition, and we learned how to solve certain problems associated with general form as well as application to infrastructure management or planning. Now, while this appears to be a good start, these Lagrange multipliers and its extensions are not free from limitations that would motivate us to look for new methods that are more efficient and generalizable to various class of problems. For example, when we talk about vanilla Lagrange multiplier setup, these multipliers are only designed for equality constraints as we learned earlier, and their adaptations with some additional conditions such as Karush-Kahan-Tucker conditions or KKT conditions would also make them applicable for various inequality constraints. However, these methods, they suffer high computational costs when we are dealing with large number of variables. Moreover, the calculations behind Lagrange multipliers and their extension, they are powered by differentiation. If you recall, we were doing partial differentiation with respect to x, y and other variables that are involved and equating them to 0. However, what to do in those particular situations when our functions are not fully differentiable, that is where we would be stuck when we are starting with Lagrange multipliers. Of course, there are workarounds on that. However, when this problem combines with the scalability, that makes choice of Lagrange multiplier based method a bit less preferable. Moreover, these are not very practical for large scale linear systems. For example, if you have objective function of form c1 x1 plus c2 x2 plus n number of variables cn xn subjected to some n number of constraints, I am writing it in compact form, we will expand it later. Let us say ax equal to b and we have m such constraints. If we want to apply Lagrange multipliers, although the methodology would not hesitate us to do so, however, this becomes impractical for large scale linear systems and may yield solutions that are sometimes trivial as we solve these set of equations. So, we needed a special class of problem solving approach that we encapsulate in the broad term of linear programming problems. So, what are the advantages of linear programming problems? So, they are very efficient for solving large scale problems. For example, when I am dealing with a problem of, let us say, infrastructure planning or agricultural restructuring, you might be hearing this word very often these days, that we have to shift from non-sustainable practices to sustainable agricultural practices, and that is where agricultural restructuring comes into picture, that instead of growing rice we should be growing millets and vice versa at the places where yield is maximum. Now, if we talk about a country of size of India, we may be dealing with 500 plus districts, and at each district we may have to deal with various constraints. There may be constraints on yield, there may be constraints on farmer income, there may be constraints on water availability. So these would constitute these large scale problems, and we would end up with few 10,000s of constraints in our optimization framework, and that is where we need an efficient algorithms to solve these problems, where linear programming problem approaches come into picture. Not only they are efficient to handle large number of variables, they are also very converse with handling large number of inequality constraints by the virtue how we would use their convexity to our advantage, go from one basic feasible solution to another basic feasible solution until we find our optimal answer. We will talk about what this word basic feasible solution means as we continue our discussion in the context of linear programming problems. In the context of infrastructure systems, these methods find great applicability for optimal resource allocation, for scheduling and planning, that is primarily applicable to many transportation system as well as water release systems, and network flow optimization, again very much useful concept in traffic engineering, water distribution system, wastewater collection system, and so on. And also we use these optimization concepts in various design problems which essentially deal with selection of optimal dimensions of constituting component involved. So these components could be individual structural component or the infrastructures constituting components like links of highways and so on. Now, how a typical linear programming problem is stated. So, we would see that this can be stated as a maximization problem, z equal to c1 x1 plus c2 x2 plus cn x1, where x, x2 and xn are of course are variables which we often categorize as decision variables, and c1, c2, c up to cn are our coefficients associated with these decision variable, which are given to us as some constants. And these are subjected to m number of constraints, a11 x1 plus a1n xn less than equal to b1 all the way till m. Now, we can have all possibilities. We can have a number of constraints m greater than number of variables, number of constraints m equal to number of variables, or number of constraints m less than number of variables. When we will talk about simplex method, we will discuss about these three cases as well, that when we would say that the problem is having some redundant constraints, or problem is ill posed, or problem is rightly posed, but we should be aware that all three possibilities exist regarding number of constraints and number of variables that we have to deal with in optimization problem. Moreover, when we talk about most of the infrastructure related decisions, we would be dealing with the positivity constraint on all the decision variables involved, because in our case these decision variable would be typically costs associated, would be typically how much manpower or human resources are needed. So that's why this positive constraint would be an additional set of constraint that we have to be mindful of to look for our feasible solutions. Now, we can always write this problem that we have written in an expanded form into a compact form, that is maximize z equal to c transpose x, where c and x are now vectors. So c can be written as c1, c2 all the way till cn, and x can be written as x1, x2 all the way till xn. So if we take transpose of c transpose and multiply it by x, we should recover the expanded form that we discussed earlier. Similarly, we can write all these constraints in the compact form as A, where A is the matrix, x is the vector, and B is also a vector, and all the positivity constraints encapsulated in form of a vector, that as all x should be greater than equal to 0, and all these problems are defined on the real domain where x is our decision variable, c is coefficient vector, a is constraint coefficient matrix and constraint bounds and so on. Now, although we have linearized all the constraints and objective function involved here, one organic question at this point that should arise in your world is that, but the world that surrounds us is typically nonlinear. We would be dealing with nonlinear objective function, we will be dealing with nonlinear constraints. So how does it apply to many of the real world situations? So in some cases, we are able to directly write the linear constraints for complex real world problems, but in some cases we make what we call as linear approximation of non-linear problems. What does that mean? Let us look into that. So non-linear relationships can often be approximated linearly over small regions. Sometimes in simple terms we also call that most of the non-linear functions can be thought of as piecewise linear. I will just rephrase it and rewrite it, piecewise linear. And under this assumption of piecewise linearity, we simplify the complex problems while retaining the essential characteristics. So when the linear programming approach is really applicable, first, when the system behaves approximately linearly. For example, if I have some function which is going all over the place or exhibit high variability, if I talk about these two x's, x and y, it may not be wise idea to work with this piece of piecewise linearity. However, if I can have a function that is indeed not just a straight line, but comprises of smooth transitions where different parts can be approximated as linear components, that is where linear programming paradigm can be used strategically. Moreover, when we talk about many real world problems, we are not necessarily behind precision, but about getting the first order estimate of our optimal analysis. When we talk about lambdas or when we talk about exact solutions that we get from systems like Lagrange, we are essentially capturing our answers, of course, accurately as well as precisely if we are able to have a mathematically tractable equations written and our functions are fully differentiable and so on. However, sometimes what happens is that for strategic planning, we need first guess and non-linear models details may be unnecessary, and in such cases this linearity approximation works very well. Of course, this comes with two benefits, that it is easier to solve and interpret these problems. Moreover, they provide insights into behavior of the system. At least the first order insights can be seen for the system. Also, when we were talking about optimization problems in general, we spoke about some very special set of functions what we call as convex function. And one advantage of dealing with convex function is that if we find a point of interest, that is if a point happens to be local minima or local maxima and our objective function happens to be a convex function, it is guaranteed that local maxima or local minima is indeed global maxima as well as global minima. So what does that mean? That let us say I have one function a like this and another function b which is again a function with some high variability as I have sketched here. Now, if I in graph A I find a point which is of interest and I establish that this point is indeed local minima using all necessary and sufficient condition tests, and this function does happen to be convex, then we can say with surety that our local minima is also global minima. On the other hand, if I talk about function b and I find that there is a point of interest where slopes are 0 and this point also meets all the sufficiency condition to be called as local minima, I could have a point which may be even lower than this, and if this function continues, I could actually miss the global minima by margin. As a result of which, I would always prefer to have my objective functions to be convex or strictly convex. Again, a quick recall, when we say that function is convex, that is, if I draw a secant joining 2 points lying exactly on the curve, if all the points on the line are above the curve about which for which I am going to test the convexity, I would be able to establish that my function is indeed convex. We also used the Hessian matrix to check for convexity and concavity, and also we can say that if a function is convex, then the negative of convex function is also concave. So, we would not worry about using word concave or convex differently in the context of optimization, because both of these functions would take us towards global maxima or global minima, whatever is the case. That is, and mathematically we say that all the points on that particular line where theta belongs to 0 to 1, you can think of it as the distance from any of the points that lie on the curve, as long as they belong to the curve or are enclosed within the curve, we can say that that the function itself is convex, and the set that is enclosed here is the convex set. Now, when we talk about linear problems, the feasible region that is defined by linear constraints is a convex set. The objective function itself is linear, and every straight line is convex as well as concave. Remember, I am not using the word strictly convex, because if you take any straight line and take 2 points on the straight line, all the points that would lie on this straight line, they are falling exactly on the curve. So, it is satisfying both the conditions, that is, points on that fall on this line L, they have values greater than equal to the curve itself. In this case, we know it is L equal to C, but for generalizability, we are writing L greater than C. Also, L is also less than equal to C, and also again we know that L is equal to C. So, by using this particular mathematical, I would say, trick in loose sense, we can really say that all the straight lines are convex as well as concave at the same time. Because because both of these constraints with greater than equal to and less than equal to signs are satisfied, which is in line with the definition of convexity and concavity that we have proposed. And its implication means that any local optimum is also a global optimum, and this does simplify the search for the optimal solutions. We will also come back to this point, that what this feasible region of linear constraints, why it is a convex set and so on. So, I will put the question mark here, but we will try to understand this with help of a graphic. So, putting this together for feasible region S for these family of constraints mentioned as Ax less than equal to b and x greater than equal to 0 is convex. And we already mentioned, for any 2 points x and y belonging to S, as long as theta x plus 1 minus theta y is contained within that particular set, we would be able to call that particular set to be convex and so on. Also, linear inequalities define half spaces, and the intersection of half spaces is also convex. So, this particular result is also well established for linear constraints. Again, when we will look into example, we will see what this half spaces are and why their intersection is always convex and so on. So, when we try to visualize this in 2 dimension, we would notice that feasible region is always a convex polygon. So, I will highlight this and we will illustrate this with help of example in subsequent slide. But in summary, what linear objective function guarantees us that linear functions are both convex and concave. In convex optimization, any local optimum is also global optimum. Also, for linear programming problems, the optimal solution would always occur at the vertices or the corner points of the feasible region. For example, if our constraints trace a region R like this, it is guaranteed that our solution would not be here, our optimal solution would not be here, but would be at the boundary points always. If you recall, I mentioned these points inside the polygon as interior point, and now we introduce another word what we call as extreme points. Of course, I can visualize all these diagrams in 2 dimensions, but for higher dimensions it would be difficult for us, and after certain number of dimensions impossible for us to draw these particular shapes or geometries. That is why we have to get good at handling the mathematical notations as they come our way in various problems. But to illustrate the various terminologies that I have coined here, let us look into one graphic representation of these equations and constraint. So, let us say that we are dealing with two constraints, x plus y equal to 10 and 0.5 x plus y equal to 8, and our objective function is that we have to maximize 3x plus 5y. So, this is our objective function. Now, what I would do is that I will draw both the constraints. One constraint I am showing in the orange line, another constraint I am showing in the blue line. And if I also further make a change that instead of equality, I am interested in that the less than equal to values of these particular constraints. Then if I focus on the orange line with an orange marker, and if I am looking for its less than equal to area, I am essentially looking at the region that I am just highlighting now. So, this is the half space of 0.5x plus y less than equal to 8. So, this shaded area is its half space. Similarly, when I talk about the blue line that I am highlighting here, its half space, if it happens to be an inequality constraint, would be this. And understand that both of these constraints have to be satisfied. So, in that case, what I will do, I will basically focus on the region of feasibility which is marked here. I will further make it prominent by highlighter of different color and say that this is the region of interest, because this is where both of my constraints are getting satisfied. And you see that the color or the area that I have shaded with green, it happens to be convex, because I can take any 2 points within this region, join them by straight line, they are always going to be inside this particular shape that I have highlighted. And this is exactly what we were trying to highlight mathematically, that intersection of half spaces of inequality constraint is always a convex set that we are now able to visualize for this particular problem in 2 dimensions. Moreover, we would always have our optimal answer either at this point or here, or in this case at this corner. In this very problem, we would see that the maximum value of this function is 42, and it happens at values of 4 and 6, which happens to be the corner point of the shape that has been traced by this green shaded area. And we will take advantage of this convexity in combination with convex sets, and would be able to scale up linear programming problems to multiple constraints and ensure that whatever answer we get is a global maximum as well. In later, when we move to higher dimension problems, we would also introduce a term what we call as a hyperplane. So hyperplane in n dimension space Rn is a flat subset with dimension n minus 1. To put it simply, line is one dimensional hyperplane in 2D space. Similarly, plane, which we typically represent by x, y, z, is two dimension. In fact, xy is two dimensional hyperplane in 3D space. That is, line is defined by y is equal to mx plus c. Plane is defined by z equal to a1 x1 plus a2 x2, sometimes x1 written as x and y2 written as y, and so on. And I already discussed about the half space. Half space is one of the two regions divided by the hyperplane itself, and it represents all the points on one side of the hyperplane, including the hyperplane itself. When we are talking about less than equal to constraints, all the points falling on the constraint itself are also part of the half space. Then another term that I would use frequently is the feasible region. So feasible region is the intersection of all half spaces defined by the constraints of a linear programming problem. So in earlier example, we saw that for these two constraints, orange and blue, this comes out, the green one comes out to be the feasible region. If I talk about these two constraints individually, this also would be their individual feasible reasons. But here I have to satisfy both these constraints simultaneously. So the feasible region would be intersection of all half spaces defined by the constraints, and mathematically we can write it as any point that belongs to Ax less than equal to b for all constraints that would constitute our feasible region. And it is the convex set when we talk about linear optimization problem, and hence guaranteeing overlap between the local optimality and global optimality. Before we go to the detailed mathematics in our subsequent lectures, it is important to see some of the use cases where linear programming problems can be used. So one very good example is emergency resource allocation, where we have to allocate limited resources to disaster affected areas, and their objective is to minimize the total response time. And there we are dealing with various parameters such as number of locations needed, total resource available, demand at location I, cost of time coefficients or cost or time coefficients for location I, or so on. So we can really express this problem for multiple locations in the linear programming framework. That is, we have to minimize the Ci xi, where we are dealing with n number of locations, and C is the cost coefficient for resource allocation at x or the resource demand itself, and it is subjected to constraints that sum of all the resources should be less than the total resources that are available to us. Also, we want to ensure that we meet the demand at each location. So we can say that at each location, the allocation should be greater than the demand at that particular allocation. In some cases, we can also argue that since we are talking about emergency allocation, why we are going to waste the resources? We should only be allocating those much resources that are needed. So in some cases, we can say that xi should be exactly equal to d, neither more nor less. And if we are talking about some non-essential goods that we need to deliver, there we can say that if xi happens to be an item which is not essential, there we would be okay to even deliver lesser than the demand. But of course, the essential goods, medicine, should be equal to or greater than equal to di. This is what we will learn with experience and handling more and more problems in the space of optimization, that how to set up right constraints and right objective function. Let us look into another example. which is related to optimal repairing schedule. Let us say that now infrastructure systems or services are disrupted after a cyclone or a flood that is induced by a cyclone or for some other reasons, then we have to schedule the repairs to restore the infrastructure services, and our objective would be to minimize total downtime. And there would be multiple tasks that would be associated. If we talk about a railway infrastructure, we may have to make sure that the condition of the foundation over which the railway line would rest is good, what we also call as sleepers are in good condition. Then the track itself would be lined up, and these tasks are also sequential in nature. We cannot lay the railway line first without checking condition of foundation and so on, and there would be some deadlines associated for project completion. So there are two things here. One is the sequence of task and one is the overall deadline. So how we can write a very simple linear programming problem for these kind of tasks is that we would like to minimize Si plus Ti, that is overall time should be minimized, and there are certain constraints that if task j depends on task I, it should not start before task I is complete. To capture that, we can write another constraint such as Si plus Ti should be less than equal to Sj, where T is the time of completion and S is the time of start of a particular task. Also, Si plus Ti should be less than equal to D, because D is the project deadline or the duration that is permissible, and of course time cannot be negative for these repairs, so all of them should be greater than equal to 0. So one worded problem now can be converted into the optimization problem very easily, and we will look into more numerical examples as we will build on this forward. So from our discussion, a few key takeaways emerge. First one is that linear programming is going to be a very powerful tool for optimizing various linear systems. And in this case, convexity does ensure that solutions are globally optimal. Moreover, this finds great application to various decision making and infrastructure resilience problems. So before we wrap up this discussion, there are few points that you should ponder upon or think about. Is that what is the area you think you can apply this linear programming problems, and how the questions about formulations would be presented. I already gave two examples from my domain, but feel free to think more that what are the various use cases you can think of where linear programming problems can be applied. In next lecture, we are going to talk about the simplex problem, and step by step we will look into one very powerful method to solve these linear programming problems, what we call as simplex method, and we will of course solve some examples, and it would be very helpful if you review some basic matrix algebra concepts, specifically how equations are solved, system of linear equations are solved, and familiarize yourself with basic optimal terminology, optimization terminology that we introduced in this lecture. Thank you.